Hello.
Thank you so much.
Are you afraid? Are you afraid?
Evet, evet. Nervous. Very nervous.
Do you know how to pronounce his name? Nicolas?
Is the person with the name of Nicolas here? No, because it's another session. And he's not here. Robert, he's not here. Okay, I'm sorry.
We are going to start this new session about geometry. Our first speaker is Muacan Akıbem. Isn't it? And also Becky Kursat Doruk. Okay, and another one. The subject is the modeling process of a paper folding problem in GeoGebra 3D.
Thank you. First, maybe I have to name my name. Muharrem. My name is Muharrem Akman. I'm from Turkey at Ahirem University. And my colleagues are Bekir Kuşat Doruk and Tolga Kabaca. Our paper titled is the modeling process of a paper folding problem in GeoGebra 3D. I don't know we use GeoGebra 3D, but I used last 1 year GeoGebra 3D, but it's better version and there are some mistakes when I use it. In this research, a problem creation which requires a lot of thinking in 3 dimensions was developed by researchers. A solution was proposed for the problem obtained by folding a rectangle paper. This figure is about my problem. I will explain this problem. You see the rectangles. Maybe think this paper. Okay. Not important. What I think. This is a rectangle paper, A4 paper, and I will determine a diamond point on the long side of the rectangle. I labeled it A value. A is here, and it's diamond point, and B is here at diamond point, another diamond point, and after we will determine another point, but this point relation with A and B. You image a virtual line. This line, A is on the line, and this line is parallel at KL segment, like this. And this new segment and ML segment intersection, we call this intersection SC. And after a new line, virtual line, B is on line, and DB parallel ML. And this second virtual line and MO intersection called B. We have 4 points on the rectangles. After we try to construct algebraic notation, after the triangles AOA and AKB, ELC and CMB are folded on the sides DA, AB, BC and EC respectively. The coordinates of the points O sub B, O sub D, K P sub D, L sub D, and M sub D must be determined. It's important to A point sub D. Find the coordinate of the point or the intersection point of the line D sub A and the line D sub O sub D will provide us to determine the coordinates of the point O sub D. Equation of the line D sub A can be calculated as follows. We want to try to find these points OD, AD, LD, and MD. But we need some equations. We found D sub dA, equation of D sub dA, and after D sub O sub D, and we determine this point. This point is OD coordinates. I use some method, another KD, LD, and MD points. And when after triangles DOA, AKB, BLC, and CMD are folded perpendicular to the floor on the sides, DA, AB, BC, and DC respectively, the coordinate points O, K, L, and M will be in their new places. Let's call these divided points as OT, KT, LT, and MT respectively. These points will be in three-dimensional space, and the coordinates of OD, KT, LT, and MD will be the first two components of them. The third component of each point will be the length of segment OOD, KKD, LLD, and MMD. These lengths can be calculated by using the points O, K, L, and the equations of the lines. After the proper calculations, the lengths are found as follows. So the order triples as the component of the points OT, KT, LT, and MT can be stated as follows. Now we have the points OT, KT, LT, and MT in space. We can think as the mathematical question in our main problem is, what's the condition for the line segments OT, LT, and KT, MT are intersected? The basic answer will be the vectors OT, LT, and KT, MT must be coplanar and not parallel. Since the position of the points OT, KT, LT, MT in space, we can be sure that these vectors are not parallel and has intersection points when they are reflected on the floor. Let's check the vectors OT, LT, and KT, MT coplanar when they are intersected in space. For this check, the fact of three vectors scalar triple product must be 0 to be coplanar can be used. We have two vectors for this operation. By choosing the vector ODKT, additionally, we can calculate the scalar triple product. I will show you, I will summarize this problem, and I will show you this application on GeoGebra 5. This is our paper, rectangle paper, and I can change its sides, length of sides, with the slider and this side. X0 and Y0 is the determine the diamond point on the sides. And Y0. We want to find location of the diamond points. Which location of the diamond point these segments will intersect. First, we think X and If dynamic point is the middle of the side, it will intersect, but it's enough only one side. I can change another side. Sorry. It can intersect. And our paper, condition of our paper, we describe this mathematically. This is called for that triple equal 0. Okay. Do you have a question? Yes.
Thank you for your presentation. Any question, please?
What's the scalar checker product? You have two options.
Okay. This one.
Yeah.
Okay. In the process, I cure 3 vectors. If the vectors lie on a plane, the segments will intersect. I say, okay. You look vectors, now vectors on a plane, 3 vectors on a plane, but if I change the vectors is not on a plane.
When they are zero, they
Zero.
will
If the determination is 0, 3 vectors on line plane.
Any question? So, thank you. Our next speaker is Petra Surikova, and his talk is about cinematic geometry.
Thank you very much. Welcome to my presentation. It's my pleasure to talk here today. In my presentation, I will present some ideas how to use dynamic GeoGebra in the teaching and learning geometry, especially kinematic geometry. So what will I talk about? Something about motivation. I have my own experiences with teaching geometry, computational geometry, descriptive geometry at Charles University in Prague. And I know that geometry can be very difficult for students, so it's necessary to increase their interest in geometry and improve the study. So I will demonstrate some ideas from the field of kinematic geometry. I will show you some special motions in the plane, and of course something about my future work. So how I said, the study of geometry can be very difficult, and one possible approach how to increase the interest in studying geometry, I think, is using computers in the teaching process. It can be interesting, motivational for students, and it's very current nowadays. So the usage of GeoGebra, I use GeoGebra for the visualization, for the proving some geometric constructions, and for the demonstration practical uses of geometry. So, kinematic geometry. This is a branch of geometry which deals with the geometric properties of objects which are created by the geometric motions. The determination of geometric motion, so we have the fixed plane and the moving plane. We can imagine that the table, the desk of the table is the fixed plane, and maybe this paper can be the moving plane. It's moving on the fixed plane. So, in the fixed plane we have there are created some routes and envelopes, some curves. So any point of the moving plane describes a curve, its path, often called roulettes, and any curve of the moving plane describes a curve. I will show you some examples, I think it will be clear. So we can see the fixed plane. There are the paths tau A, tau B, tau C, and the moving plane in the two positions. There are points A, B, C. So the determination of the motion in the plane, there are many possibilities how to determine the motion. So, for example, by two paths of 2 points, it's the example on the left, or by two envelopes of 2 curves, for example, 2 circles. This is this example. Or we can combine these determinations, so we can have envelope and some paths of points. The envelope and the path. Then the motion is given by, for example, envelopes which can degenerate into points, and also we can combine it. So is the path and the envelope. I think you know this example of the determination of the geometric motion, and it's by the centroids. We have the fixed centroid and the moving centroid. This curve, the moving centroid is rolling by the fixed centroid without the slipping. And this is the typical example of this motion. The wheel is rolling by the straight line without slipping. So I created a database of some examples of motion in the plane. You can see my web pages. There are examples of these situations. I provided the access to this database for my students, and also my students can create some dynamic worksheets, and I place it on my web pages. So I will show you some examples. How I said, the determination of the motion can be by 2 envelopes. So here you can see 2 circles, 2 envelopes of 2 straight lines. This is the motion, geometric motion. You can see the point A, and the path on this page, on this point, is the green curve. Of course, you can change some parameters, radius of circles, and so on, the angle of the 2 straight lines. My students have to construct the results of the curves and the envelopes and the paths by hand. And sometimes it's very difficult to imagine how these curves look like. So this dynamic worksheets can be very suitable as to imagine the situation in the plane. Another example, very typical example of geometric motion. The circle is rolling on the fixed straight line. Without slipping. In every moment, this straight line, this segment, has the same length as the circle, as the arc of the circle. And you can see the classes of some points. Of course, I can change the parameters. You can see the results. So this motion is example of very special motion in the plane. It's cycloidal motion, and how I shown it was the moving centroid is the circle and the fixed centroid is the straight line. Another example is involved motion. A straight line is rolled on a circle. It means that the moving centroid is the straight line and the fixed centroid is the circle. Another example, epicycloidal motion. A circle is rolled on a second circle. We have three cases. Epicycloidal motion is obtained by rolling circle on the outside of the fixed circle. I will show you the example. Hypocycloidal motion, it's another example. This motion is obtained by rolling the circle in the fixed circle. And the last one, paracycloidal motion, by rolling the circle on the outside of the fixed circle, which is inside the rolling circle. So, example. This example is quite interesting because it was quite difficult to construct in GeoGebra because in GeoGebra we can define the angle only between 0 and 2 pi. But I need to go around the circle for more times, so I define new parameter. Omega. I can go around the circle for more times. And you can see the results of the motion, different paths, epicycloids, spheroid epicycloid, and curvature epicycloid. And of course, we can also change the range of parameters in the parametric description of the curves. So I show you some different example. I change the radius of the circle. Very nice pictures of the path. There exists a wide range of very special motions in the plane, the elliptic motions, cardioid motions, and conchoid motions, but I talk about the most important Oedipus now. And I think I can say that the responses from students is very positive. I think they thought that they think that the geometry becomes modern discipline, more understandable, which if they use GeoGebra, and I think it's very motivational and attractive for them. Also, my students create some various outputs in GeoGebra, and in future work I want to extend our gallery at my web pages. So I hope that there will be more examples from the kinematic geometry. And if I have more time, I can show you some more examples. How I said, this motion is determined by two envelopes, two circles, and we can also find the fixed centroid and moving centroid. If I will move with the point, we can change this motion for the moving centroid on the fixed centroid. So it can be the last example. Thank you for your attention.
Thank you for your presentation. Any question?
Researchers and students are visiting the pages. Are they just browsing like a guy and
Yes, yes, and also they created some examples themselves, and I place it on my pages.
thank you.
Any other question?
As a high school teacher, I'm interested in an elliptic motion. I think you have mentioned Reader has any model.
Yes, elliptic motion is a very nice example of is a geometric motion in the plane. It can be determined. It can be given by the moving centroid in the fixed centroid, and it's a circle, and the circle is double radius. I will move with the point. You can see the elliptic motion, and the path of every point is ellipse. But the point on the circle, its path is the straight line, the second. Also, I can change the radius of the circles. You can get some another examples.
Any other question?